Let's take a look at problem number 49, chapter 6 in Wade 9th edition. In this case, we have three molecules, two of which racemize and one does not. So let's take a look at the mechanism for this. In the first one, we have an optically active alkyl bromide. I'm just picking the bromine wedged over here, but it could have been dashed either way. We have this in potassium bromide, aqueous potassium bromide. Now, aqueous potassium bromide means that we're going to have a solution here. So you're going to have Br minus ions floating around, you're going to have K plus ions floating around, and you're going to have H2O molecules floating around. Now, in this case over here, this is going to undergo an SN1 mechanism because water molecules are going to, polar water molecules, protic delta minus, delta plus, there's going to be some intermolecular force between the bromine substituent and water, the protic water, pull off those electrons, and now we're going to get a secondary carbocation, and we're going to have water molecules around, but we also have, in this case, we have a higher concentration of bromide ions because we have potassium bromide. So we have Br minus and K pluses. If we had a high concentration of water and a low concentration and no extra bromide, then water molecules will come in. But if there's a high concentration of bromide because of the potassium bromide that was put in there, the bromide is going to be more attracted to that carbocation than water will be. And since this is a flat carbocation, the bromide is going to come attack from the front or from the back. So we're going to get a racemic mixture. We're going to get replacement bromide that and replacement bromide here, racemic mixture. In the second case, we have an alcohol and we have a base. Now here we have K plus, we have OH minus, we have K plus ions, and we have water molecules around. Always ask yourself, do I have any negatives anywhere? And I do. This is under basic conditions. There's a difference here. This O oxygen is going to go ahead. I have a delta minus, delta plus right here. This will pick up that hydrogen, dump these electrons onto that oxygen, and now we're going to have an intermediate, a negatively charged oxygen, and water molecules. And still K plus, and more water molecules. The only thing that can happen over here, now remember, the K plus is going to be a spectator ion because potassium always wants to remain positive. So the only thing that can happen over here is that this will come right back and go right back to the starting material. So actually, I won't even draw that. This is going to go back and forth. There is no breaking of any bonds with the carbon-oxygen bond is not broken in this case, so stereochemistry is maintained. Whereas in the first one, the SN1 mechanism right here, the carbon-bromide bond is broken, and so now we're going to have that carbocation intermediate. So in this case, we retain stereochemistry. In the last case here, this one's a little bit different. This is under acidic conditions. We have H plus and H2O, weak acid. The driving force over here, if you have a negative, we don't have any negatives, but we do have a positive. We have the acid, which is positive. This is going to be the driving force. It's going to suck electrons at it. This oxygen is slightly negative. It's going to pull in that right there and protonate our alcohol. So now our first step is going to be the protonated alcohol. I'm circling the hydrogen that it picked up. Now, this becomes a really good leaving group. So this is going to be an SN1 mechanism. the oxygen, the positive oxygen is not happy. It's going to pull off, and we're going to get a carbocation intermediate, secondary carbocation intermediate. Rearrangements are not beneficial in this case. If we steal a hydrogen from here, there would still be a secondary carbocation. And we have water molecules. And so now the slightly negative oxygen is going to get sucked into the carbocation. But once again, this is a flat carbocation. So the water molecule is going to attack from the front and from the back. And we're going to end up getting a racemic mixture, racemic substitution. So you'll have a water molecule attacking on the back side, a water molecule attacking on the front side. And then both of these will get deprotonated by another water molecule to give us our final racemic mixture, where we have, we're just going to, instead of drawing, it's going to be a 50-50 mixture, OH and wedged OH racemic mixture. So the key is, here we got SN1. SN1 mechanisms lose stereochemistry. SN1 mechanisms lose stereochemistry.